By magnetizing a piece of iron or nickel or cobalt, okay, we'll stick with iron just because, all right? By magnetizing it, we force all of those little blobs that are stuck together in the metal, we force their kind of magnetic direction to point in the same direction as all the other little pieces that make up that piece of metal. And by doing that, notice how all those arrows are pointing to the right, okay? By doing that, by forcing them all to point in the same direction, that's how we create magnetic poles, where one end of the magnet ends up being the North Pole, and the other end of the magnet ends up being the South Pole. So the direction at which the arrows are pointing, like this, becomes the magnetic north, okay? So becomes the North Pole of that magnet, whereas the opposite end becomes the South Pole. Does that make sense? Anytime you have a magnetic piece of metal, okay, we call it a ferromagnetic piece of metal, it will have a South Pole and a North Pole. Okay? They always have both, and they are at opposite ends of one another. Now, the interesting thing about that's the lower box here, it's one solid box. Okay, it is one solid piece of metal. It's one magnet. Now, if you're walking along and you drop this magnet and it shatters into, let's say, we'll call it 3 specific pieces. Okay, a big crack appears right here. Another crack appears here. So we're left with 3 individual pieces. Okay, there's where we started out, and there's the broken piece. Okay, there's one. Here's the next broken piece. All right, and then here's the final broken piece. Right? There's my 3 pieces of that original magnet. Well, this is going to remain the South Pole of that original magnet, and this is going to remain the North Pole. But here's the deal. Now, this one big magnet is now broken into 3 parts. So wherever that small little part ends, the opposite end from the actual south here, this is going to become the north end of that piece, because it's as far away on that piece from the south. Do you see that? So, same goes for this, because remember, in this actual piece, the actual domains were all pointing in this direction, okay, from the south towards the north. So then in this new middle piece, this is going to be your south, this is going to be your north, because remember, originally, all the domains are going this way. And then what do you think is going to happen here in the last piece? It's going to be south, exactly, because we're maintaining the fact that the domains are traveling in that specific direction. So before we move on, we're just going to make a nice little compare and contrast here between static electricity and the idea of magnetic behavior, because there are some similarities, okay, but there's also some differences. So they both, when we're talking about static electricity, they both behave along the lines of likes or similar charges or similar poles will repel one another, and opposite poles and opposite charges will attract one another. That is one similarity, okay? And that's pretty much the only similarity, because their main difference is that they're 2 completely different things. Okay, electric charge deals with an overall positive charge if you've got more protons than electrons, or a negative charge where you've got more electrons than protons. Whereas magnets deal with the direction that those little domains are pointing in. Okay, so if the domains are pointing away from you, from that end of the metal, it's the south pole. If they're going towards the part of the metal that's magnetized, it's the north pole. You cannot substitute positives and negatives when we're talking about magnets. Okay, so one difference is that these guys deal with positive and negative charges, and these guys deal with north and south poles. Okay? We're going to draw, so we've just drawn a magnetic field, or an example of a magnetic field. I'm going to make this a little smaller. Move it over here. And we're going to look at a horseshoe magnet. Okay, the U-shaped magnet, because that one is kind of interesting. We know that a horseshoe magnet has two poles, same as any other magnet. We'll call this pole the south, and we'll call this pole the north. So we know that the north pole of a magnet is where the magnetic field is going to leave from. And it's going to leave in 3 dimensions, all around the tip of that magnet. So, where is it going to want to go to? Where is it going to want to go? It's going to want to go towards the south of that magnet. So in this case, some of them will, okay, some of these little arrows will come out of the north and they'll come this way, just because they come in 3 dimensions. These guys tend to get a little bit lost, okay? But as the other ones come out, they're going to be attracted towards the actual south pole of that magnet, okay? Now, when we look at a horseshoe magnet, is the bottom part down here magnetic at all? It's not. It's actually not magnetic at all. So nothing really happens down here in that horseshoe magnet, okay? All the action is at the end of the U, at both sides of that U. And what ends up happening is not only is the tip magnetic, okay, so not only is this section really magnetic, but this part is also somewhat magnetic, just like this part is also somewhat magnetic. So that's why we see that in addition to them sprouting out of the top, they're actually coming out of the sides as well to a certain extent, and they're attracted towards the southern side of that horseshoe magnet. Okay? The horseshoe magnet is really the only kind of oddly shaped magnet that we're going to be looking at. So that's why I really wanted to draw this guy. Okay? Now, when we've got 2 bits from the same, two magnet ends that are of the same pole, what do they do to one another? They repulse. So if we've got, and you can use the idea of the magnetic field to explain their repulsion. Okay, so if you've got 2 little pieces here, and both of them are, let's say, north, well, we know that on this magnet, the magnetic field is going to come this way, right? It's going to go all the way around this guy, right? Well, the same thing's going to happen to this guy. It's going to go all the way around to the other side of the magnet, okay? So when you actually try to push these magnets together, there's that resistance. And the resistance has something to do with the fact that these 2 magnetic fields here are bumping into one another. And they're like, whoa, I need my space here. Okay, back off. That's why they don't attract to one another. What ends up happening when you've got 2 opposite ends pointed towards one another, this north is going to go to the closest south. So everything that's coming out of the north, like this, is going to then go into the south that's as close to it as possible. And that's why these two magnets attract one another. Okay? Because that magnetic field is wanting to go towards that south. It's drawing it towards it. So now that we understand how magnetic fields work, we're going to look at how magnets can impact compasses. Because at the end of the day, a compass is nothing more than an actual needle that is ferromagnetic, which means that needle that's in a compass is a small little magnet. And what ends up happening is that when we actually have a magnet like this, and we've got that north pole here of the magnet, the interesting thing about this is this little needle here ends up being kind of like affected and drawn when closer magnets appear. If there's no magnet in and around the actual compass, the compass's magnet or the needled magnet will be attracted by the Earth's magnetic field. But if I actually bring a magnet in close to this, and I have my north here and my south over here, I am going to affect the way this magnet actually behaves. In that the magnet, the actual north pole of this magnet here, is going to want to get as far away from the north pole of this magnet. The end result is going to be something like this, where you're going to have your north pointing in the absolute opposite direction of your bar magnet north. The same can be said for any other type of actual magnet. So let's draw, let's say, a bar magnet here, having our north on one end, our south on the other, and if we place a compass right along the bottom of them, the compass is going to actually be drawn away from the actual north. Okay, it's going to want to go, and that might actually even be horizontal here. It's going to want to go as far away from this north pole as it possibly can. If you've got, let's say, a U-shaped magnet, so if we erase this and we draw in a U-shaped magnet, okay, we've got our north over here and our south over here. If I plant my compass in right here, it's going to want to go basically as close to north as possible. So it's going to, the north needle is going to want to get as far away from the actual north of the compass as possible. So if you want to practice this, do you have an idea of where this would end up? Same goes for something like this. What if we then put the compass down here? What direction would the needle go? Okay, if we put the compass over here on this bar magnet, what direction would it go? So practice these. If you have any questions, come and find me.